All right, welcome to Chapter 11 in our physics class, where we are talking about oscillation and waves. So we're going to start off by talking about a type of apparatus here that's set up where we have a block attached to a spring on a horizontal frictionless plane. And what we can do with this type of setup is we can pull the block away from the point where the spring would be relaxed, and it requires a force to do that. And it puts some stored potential energy into the spring, and then we let it go. And what happens when we let it go is that the spring wants to return to its original relaxed state, so it moves the block to the left, but it doesn't immediately stop at that relaxed point. It shoots right past it to the left, and then the spring gets compressed. So again, it's being stretched a distance x away from its point where it would be at rest, and so we have put potential energy back into that spring, and then it wants to expand back out. It's going to push the block back to the right to try to get back to its original point, but it is going to shoot past that point and then stretch the spring out. And this process is just going to repeat. It's just going to go back and forth and back and forth and back and forth. And if there's no friction, then this would theoretically just keep going on forever and ever. And this would be an example of a simple harmonic oscillator. An oscillation is basically just a type of motion that gets repeated, and it would just keep going because the spring and the mass of the block keeps restoring the energy back into the system. So the energy essentially just gets transformed back and forth between kinetic and potential energy. So if we look at this situation in a little bit more detail and start to quantify this idea, we have to look at the spring energy, the energy stored in the spring, or the force required to stretch or compress a spring. And whenever we're talking about springs, we're talking about our old friend Robert Hooke here, Isaac Newton's enemy. So Robert Hooke is the one that investigated springs and came up with this relationship that the force required to stretch a spring is equal to negative kx, where x is the distance from the point of where the spring is in its relaxed state. So if I were to draw my spring here, if this is the length it wants to be in its relaxed state, and then I stretch the spring out to here, x is the distance I have stretched it. So I've stretched out some distance x, and then if I multiply that by a spring constant k, that will tell me how much force was required to stretch it that distance. And this k is different for every spring. It really is a measure of how stiff or strong the spring is, the way it was made. So there are some springs that require a lot of force to stretch them out. There are others like slinkies that require very little force. They're quite easily stretched out. So again, if we look at our simple harmonic oscillator here, we have here is where x equals 0. So this is where the spring wants to be in its nice relaxed state. Okay, and here the spring has been compressed, and the distance x that it's been compressed to the left is equal to negative a. Capital A, is what we're going to use to describe the amplitude. So the amplitude is basically the maximum distance, x, that our simple harmonic oscillator can be stretched out. So when the spring is compressed to its maximum compression, and this box is the farthest away to the left from its relaxed state, we can say that x equals a, or in this case negative a, because it's to the left. And then this compressed spring wants to push it back out, and for a split second, for just a split second, the spring is in its relaxed state. But of course, it can't just stop immediately. There's no friction here, and there's nothing to really stop the spring, so it wants to go back to this point, but it shoots right past it. It keeps going right on until the spring is stretched out to its furthest point, where x equals a. This is the maximum amplitude a, where the box is stretched out all the way to the right. And then the box comes to a stop, and then it goes back and forth and back and forth. And that back and forth type of motion is called oscillation. So displacement is measured from the point where the spring is in its relaxed state, x equals 0. Amplitude is the maximum displacement. A full cycle is to and fro. So if we started in the compressed state, the box would have to go out to the point where the spring is relaxed, then where the spring is fully stretched, and then back to the relaxed point, and then back to the fully compressed point. This right here, this full series of diagrams, A through E, represents one full cycle. The amount of time required to make that cycle is a period, just like when we were talking about circular motion. And the frequency is how many times the cycle repeats itself per second. So if we, again, this is just sort of a review here of the Hooke's law when it comes to springs. If we apply a mass to a spring, the gravity is going to pull it down. This is actually the reason why when we look at a simple harmonic oscillator that we have set up, it's on a horizontal surface so that gravity doesn't bring it to a stop. Because if our oscillator was vertical like this and we stretched it out, yes, the mass here would bounce up and down a few times, but then eventually gravity would bring it to a stop. So it would eventually come to rest here, and this would not be an example of a simple harmonic oscillator. But in this particular case, in the vertical direction, the force being applied, it would be equal to mg. Mg is the force pulling it down, the force in the spring pulling it back up. Eventually it would come to rest and be in a state of equilibrium. And the distance here, x, that it gets stretched out, if we would multiply that by the spring constant, would be equal to the force, which again is equal to mg. That's just a little, again, review or background on springs, and also illustrates why our simple harmonic oscillators are oriented horizontally and not vertically. Okay, so the simple harmonic oscillator, in order to be considered a simple harmonic oscillator, has to have a restoring force. There has to be some force present that is going to bring the system back to its original starting point. In our case here, with the spring setup, that restoring force comes from the potential energy stored within the spring. That potential energy gets turned into kinetic energy, and then that kinetic energy gets put back into the spring as potential energy, and the system just repeats itself. Now I think I've got an animation here. Yes, see, it goes to the right, and then that would stretch out a spring. If we had a spring that started here at the 0 point, and it would get stretched out at this extreme point where the displacement is equal to the amplitude, the box would come to rest. So all of the energy is now in the spring as potential energy, and then that potential energy would get transferred back into kinetic energy, and the box starts to move to the left. Now for a split second, when the box is back here at its original resting point, all of that potential energy has been turned into kinetic energy. So at this point right in the middle, we have all kinetic energy, 0 potential, but then we shoot right past it, and then we reach this point over here to the left where the box comes to a rest, so our kinetic energy is 0, but now all of that energy is back inside the spring as potential energy. And it just keeps repeating and repeating. Okay, let's just look at a simple spring equation problem here, where we have a family of 4 that has a total mass of 200 kilograms. They're going to get into their car, which has a mass of 12,000 kilograms, and the springs are going to compress 3 centimeters. What is the spring constant of the car's springs, assuming that it acts as a single spring? So all 4 will compress equally. And how far will the car lower if it's loaded with 300 kilograms instead of 200? So there's a bit of information here that really it is unnecessary, and that is the mass of the car. We don't know how much the car's springs have been compressed by the weight of the car itself, but whatever that amount is, it's already been done. Before the family gets in, the springs are already somewhat compressed. And so the mass of the car is really irrelevant to our problem. Essentially, what we're interested in knowing is how much more the spring compresses due to the mass of the family. So we want to convert that mass of the family into a force. So force is equal to mg, and the mass of the family was 200 kilograms. And if we multiply that by the acceleration due to gravity, which is 9.8 meters per second squared, then 200 times 9.8 gives us 1960 newtons. Okay, now according to Robert Hooke, the force in a spring is equal to the spring constant times x. If x is what we want to know, then actually no, x is not what we want to know. We know x. We know how much springs are going to compress. We want to know what is the spring constant. So negative k is equal to force divided by x. So the force is 1960 newtons, and we're going to divide that by how much did it compress. And if I back up here, how much did the spring compress? 3 centimeters. Okay, so 3 centimeters, let me write this down, 3.0 centimeters is equal to 2, move that decimal place 2 places, it's equal to 0.03 meters. So 0.03 meters. So 1960 divided by 0.03 gives me 6.5 times 10 to the 4th, right? Is that right? I think so. And those units are Newton per meter. That's the spring constant. And then if we wanted to know how much the car would stretch if the family gained some weight and was 300 kilograms, it would be F divided by K, which now if the force is 300 kilograms and the spring constant is the same, 6.5 times 10 to the 4th, then this would work out to be 4.5 times 10 to the negative 2nd meters. Okay? All right. We'll resume this discussion in the next video.